Welcome to the world of exponential decay. From the cooling of your morning coffee to the breakdown of carbon isotopes in ancient artifacts, nature follows a predictable mathematical rhythm. Today, we will explore why these processes slow down over time and how calculus allows us to predict exactly how much of a substance remains at any given moment. Understanding decay isn't just for physicists. Doctors use these equations to determine how long a life-saving drug stays in your bloodstream, and engineers use them to ensure structural safety. By the end of this lesson, you will see the hidden calculus that governs everything that fades, cools, or diminishes over time. Before we dive into decay, remember our friend E, the natural base. In calculus, E is unique because the derivative of e to the x is simply e to the x. This makes it the perfect tool for modeling continuous change, where the rate of growth or decay is directly tied to the current amount present. Recall that a derivative represents a rate of change. If we say a substance is decaying, we are saying its derivative is negative. Specifically, in exponential decay, the speed at which you lose material depends entirely on how much material you have left. The more you have, the faster it disappears. This is the heart of decay, the differential equation dn dt equals negative kn. It states that the change in amount n over time t is proportional to the amount n itself. The constant Ka represents the specific rate of the substance. This simple relationship is the foundation for all exponential decay models. By solving the differential equation using integration, we arrive at our primary function, n of t equals n0 times e to the power of negative kt. Here, n0 is your starting point. Notice the negative exponent. This is what ensures the values decrease as time moves forward, rather than growing toward infinity. Look at the shape of this graph. It starts steep, representing a rapid loss when the amount is high. As the amount decreases, the slope flattens out. Mathematically, the curve is asymptotic to the x-axis, meaning it theoretically never reaches zero, even though it gets incredibly close over long periods. The constant K determines the personality of the decay. A large K value means the substance vanishes quickly. Think of a hot spark cooling in snow. A small K value means a slow, lingering decay, like the radioactive breakdown of uranium-238, which takes billions of years. A common way to describe decay is half-life. This is the time it takes for exactly half of the substance to disappear. Interestingly, this time interval is constant regardless of how much you start with. Whether you have a gram or a ton, the time to lose half remains the same, dictated by the constant K. Let's put this into practice. Suppose we have 100 grams of a carbon isotope with a decay constant of 0.00012. To find out how much is left after 1,000 years, we simply plug our values into the formula. We multiply the constant by the time, negate it, and apply it as an exponent to e. First, we calculate the exponent, negative 0.12. Then, we find that e to the negative 0.12 is approximately 0.887. Multiplying this by our initial 100 grams, we find that 88.7 grams remain. This means about 11.3% of the substance decayed over that millennium. Calculus gives us this precision. What if we don't know K? Suppose we start with 50 units and after 10 minutes, only 25 remain. We set our equation to 25 equals 50 times e to the negative 10k. Dividing both sides by 50 gives us 0.5, which makes sense because half the substance is gone. To solve for k, we take the natural log of both sides to cancel out Li. The natural log of 0.5 is approximately negative 0.693. Dividing by negative 10, we find that k is 0.0693. We now have a mathematical model that can predict the amount at any other point in time for this specific substance. We can also find the instantaneous rate of change. If we want to know exactly how fast the substance is disappearing at minute 5, we don't use the original amount, we use the amount present at minute 5 multiplied by our decay constant k. This gives us the speed of decay in units per minute. A fascinating variation is Newton's law of cooling. Instead of decaying toward zero, an object's temperature decays toward the surrounding room temperature. The math is identical, but we shift the graph vertically by the ambient temperature. It proves that the hotter the coffee, the faster it loses heat. In cases with an extremely large k, decay happens almost instantly. In the macro world, this looks like a sudden step function. However, calculus reminds us that even these sharp drops are continuous curves if we zoom in far enough. There is always a finite, measurable transition. Conversely, if k is nearly zero, the substance appears stable. For example, some isotopes have half-lives longer than the current age of the universe. To our eyes, the rate of change is zero, but the calculus of decay tells us that on a long enough timeline, everything changes. In advanced physics, one decaying substance might turn into another substance that is also decaying. This creates a system of differential equations. The amount of the middle substance increases as the first one breaks down, then decreases as it decays itself, creating a hump on the graph. We must remember that calculus treats decay as a continuous flow. In reality, at the atomic level, atoms pop out of existence in discrete steps. However, because there are trillions of atoms, the smooth curve provided by calculus is an incredibly accurate approximation for all practical purposes. One of the most frequent errors is forgetting the negative sign in the exponent. Without it, your model will predict that your substance is growing exponentially rather than decaying. Always check your graph. If the line is going up, your k or your exponent sign is wrong. Another trap is mismatched units. If your decay constant k is defined in a year, but you plug in its t value in a days, your result will be wildly incorrect. Always ensure that the units of your rate and the units of your time variable are perfectly synchronized before calculating. Students often confuse the base 2 used in simple half-life logic with the base e used in calculus. While they describe the same reality, you must use the natural log of 2 to convert between a half-life and the decay constant k used in our primary formula. Let's recap. Exponential decay occurs when the rate of loss is proportional to the current amount. This leads to a predictable curve defined by the natural base e. The decay constant k and the half-life are two ways of describing the same speed of disappearance. Think about this: if you start with 100 grams and the half-life is 5 years, how much is left after 10 years? Since 10 years is exactly 2 half-lives, you would halve the 100 grams once to get 50, and then halve that 50 again to get 25. The answer is 25 grams. Whether you use simple halving or the full calculus formula, the result is the same. You now have the tools to model and predict the fading world around you. Keep exploring the patterns of change. Generated by Vision Solve AI.